center of mass is 1 over the total mass of all of the objects. That's the sum of xi. So take the x component of each position, multiply by the mass that resides at that place, add them all up, and divide by m, and that gives you a kind of average of all the parts. It's weighted by their respective masses. So heavier mass counts more in taking the average. That's the x component of the center of mass. If you're working in 2 or 3 dimensions, there's a y component of the center of mass, in which you would have capital Y here, and a little y here, and the z component. I'll write those all at once. The 3 component of the center of mass in 2 or 3 dimensions would be the vector center of mass position equals 1 up to n of mi times ri, where ri now would be the vector position of that particle. So particle number 1 and particle number 2, and so on. So that's for 2 or 3 dimensions. And if you have a continuous distribution of matter, a potato here or something, instead of discrete point masses, then I say the position of the center of mass, this just converts over to an integral. 1 over the total mass times the integral of x dm. We'd rather chop the thing up into little infinitesimal pieces. Here's one of them. There's mass dm, multiply it by its x, the x component of its position, and integrate them all up. And that will give you the center of mass for a continuous distribution. I'm going to run a more complicated example now to begin with. You know, it used to be the case that a calculus course, a first-year calculus course, you would spend about a month and a half calculating the center of mass of every conceivable geometrical object. This seems to have gone out of style now. In fact, even in the physics books, they don't do much. Our textbook, I don't think, does a single, no, does in the back of the book, there's one example of a problem where you calculate the center of mass actually by doing an integral. This is a big change. And I think it's a mistake, actually. Every student of physics ought to know how to calculate center of mass. It's actually a very lovely application of integral calculus, apart altogether from its physical importance. So I'm going to do you here an example, and you get to do an example on the homework also. Example of a calculation of center of mass for a continuous distribution of mass using this formula here. I'm going to find for you the center of mass of a uniform hemisphere. I'm not going to do a uniform sphere, right? Because the center of mass of that is obviously at the center. So it's got to be something a little more interesting than that. Find the center of mass of this uniform hemisphere. Let's give it a radius r. Watch how this goes. Very interesting calculation. First of all, if I had a hemisphere here, take the globe, slice it in half. I've got the hemisphere here. That thing, that center of mass obviously lies on the axis of symmetry of the object, isn't it, right? So there's only one component that I need to calculate. I'm going to stick this hemisphere in this configuration here. So here's the axis of symmetry. The x-axis is the axis of symmetry, and it looks like this. Whoops. See if I can draw that. Does that look sort of like a hemisphere here, sticking out to the right? Put a little bit of shading on it, so it actually looks a little bit like a hemisphere. You got a picture? This is solid, by the way, not a hollow hemisphere. I'm not talking about a salad bowl. I'm talking about a baseball that you slice through, and here right-hand half of it. How do we do this? What I want to do is calculate x equals 1 over the total mass times the integral of x dm. What I have to do first is chop this thing into slabs, each one of which has a particular value of x. So here's a slab. I run this thing through a bread slicing machine or something, and here's one slice of bread there. You see it? It's all over at a distance x, and it has a thickness, let's say, dx. It has a radius, let's call it r, and now I ask you, what is the mass of that slice of bread? My drawing is not that hot. I've practiced this, but I can't get it to come out looking like what it's supposed to look like. But can you visualize this? There's a hemisphere over there pointing to the right. I cut a slice out of it, a pancake here, which is out at distance x from the YZ plane, and it has a thickness dx. Question, what's the mass of that slab? dm the mass of that slab is, what would you say? Mass per unit volume times the volume of the slab, isn't that right? So let's figure out what those two terms are. What is the mass per unit volume for this hemisphere? Mass per unit volume would be the total mass of the whole thing divided by the volume of the hemisphere. Anybody know what the volume of, well, how about a sphere? Do you know what the volume of a sphere is? 4/3 pi r cubed, very good. But this is only a hemisphere, so it's half that, so it's 2/3 pi r cubed. So I happen to know that the volume of a sphere is 4/3 pi r cubed, so the volume of a hemisphere is 2/3 pi r cubed. So that's the mass per unit volume, the total mass of the whole thing divided by 2/3 pi r cubed. Now, what is the volume of my slab? This is a slab of radius r, of thickness dx. So what would you say for the volume of the slab?
Pi r squared times
Pi r squared, that's the area,
times dx.
times dx, that's the thickness. Good. Yeah.
But if this is the volume if dx is very, very small, because
Indeed,
it will
indeed,
have-
because otherwise there's the tilting edge there, and it wasn't really off. So I'm talking about, in the calculus sense, always the infinitesimally thin slab here. In the limit, I'm going to take a slab that had no thickness at all, or infinitesimal thickness, and
So radius
add them all up. So in that sense, the radius, the point is that the radius is slightly smaller on the right-hand edge than it was on the left-hand edge, but I'm making those things so thin that it's essentially just pi r squared times dx. So what is the dm here? Is mass per unit volume, I'll bring the 3 up on top, 3m over 2 pi r cubed. That's the mass per unit volume times the volume of this little slab, which is pi r squared dx. So far so good? I think I cancel the pi's here, and now I'm ready to stick this into my integral. X is equal to 1 over m, 1 over the total mass, times, actually I'll pull all this stuff outside of the integral, 3m because it's constant, over 2 r cubed, 3m over 2r cubed. And what's left is the integral of x, don't forget that, times r squared dx. M's cancel. And now I'm stuck. How do I do the integral of x times r squared dx? I got two different variables under the integral sign. I've got to substitute r squared in favor of x. How is r related to x here? Maybe I better draw this diagram in profile here. Here's the circle. Here is x. And here is r. And of course the radius of the sphere is capital R. So what's the connection between little r and x? I guess from the Pythagorean theorem, x squared plus r squared is equal to capital R squared, the radius of the whole sphere. Does that make sense? There are a number of different items that go into this calculation here. So I'm trying to treat each one of them separately. X squared plus r squared equals capital R squared because this is a sphere. So the x component plus the r component squared is equal to capital R squared. So r squared, in other words, is equal to capital R squared minus x squared. Capital R, of course, the constant, that's the radius of the sphere. X is now what I was trying to integrate with respect to, so let me put this in now. 3 over 2r cubed, and I have the integral of x times r squared, which is nothing but capital R squared minus x squared, and I'm supposed to integrate that with respect to x. Now this is set up as a well-defined integral that I can do. What are the limits on that integral? The range of x in this problem.
From 0 to r.
0 to capital R, because it starts here and goes out to here, it starts here, goes out to here, so x runs 0 up to capital R. Now I have a well-defined integral to do. Let's just calculate it. It's 3 over 2r cubed. Now, let's see, can we do that integral? The first term is x times r squared. R squared is just a constant. The integral of x, 1/2 x squared. The next term is minus x cubed all told. If I integrate x cubed,
1/4 x.
x to the 4th, 1 higher power over 4. So this would be x to the 4th over 4, and I'm supposed to evaluate that at the limits 0 and capital R. So let's put those in. When I put in x equals 0, I'm going to get nothing, so it's only the upper limit that gives me anything. 3 over 2r cubed times r squared, and another r squared, so it's r to the 4th, over 2, minus over here, r to the 4th over 4. That whole thing is r to the 4th over 4. 3 of the r's cancel, and I get 3 over 4 2s are 8 r. There's the answer. Does that answer seem reasonable? It says that the center of mass of this sphere, of this hemisphere, is 3/8 of the way out to here. A little bit less than halfway, so about there somewhere. Seem reasonable? If I had done this calculation and I come out with r over 2, what would you say? Gotta be wrong. There's no way that this could be halfway out there. Still less that it could be larger than that. It certainly is going to be somewhere in the left-hand half. 3/8 sounds like a reasonable answer to me. And it happens to be correct. How many of you followed that argument? Most of it? Good. At your leisure, you can go down and each of the individual pieces that goes into it. It's not that tough, I think. But the whole calculation has a lot of pieces to it. So complexity, as I say, you get to do, well, you get to do a problem that in a way seems like it's simpler, a semicircular plate. This is just a two-dimensional problem, not the full feed, but you take a dinner plate and slice it down the center, so you only got half of it. Where is the center of mass of that thing? Certainly going to be a little less than halfway across, but exactly how far across? Not 3/8 are. That's different. It turns out, in some respects, it turns out to be a little bit more difficult problem. It's easier to set up, but the integral is slightly more difficult. If I have time again today, I'll come back and start the setup of that problem. But I want to move on now to the formulation of mechanics for a system of particles. What is all this center of mass stuff good for anyhow? So, I have in the back of my mind the following situation. I've got a bunch of particles, each one with a particular mass and a particular location, and they're moving all over the place. I don't know, this is very general. I'm not assuming that they're locked to each other or anything like that, or they're forming a rigid object. In fact, what I have in the back of my mind is a swarm of bees. There are a bunch of bees, and they're flying around every which way. So here they are. Bunch of them. This is bee number 1, has mass m1, and it's right at the moment when I took the picture, out of position r1. And then there's bee number 2, whose mass is m2, and that's at r2, and b3 at r3, and so on. Got a picture? And then those things are buzzing all over the place. So as time goes on, they're moving around in some complicated fashion. This down here is just the origin of my coordinate system. So, what's the center of mass of that swarm of bees? Here we have it. It's a full three-dimensional problem. 1 over capital M, that's the total mass of all the bees, times the sum of bee number I times its position, Ri. That's the center of mass of the swarm. Do you want me to put I equals 1 to n on here over all of these? I usually leave that off. The sum just means sum over all of these. Now, what I propose to do is calculate the derivative of that with respect to time. How does the position of the center of mass change? Or, if you like, what is the velocity of the center of mass? This is the position of the center of mass, but as time goes on and the bees move around, that center of mass itself moves around, and I'd like to know what its velocity is. V, I use capital letters to denote the center of mass, or things that pertain to the whole object, the center of mass, the total mass, capital letters, and little letters to talk when I'm talking about the individual particles. So V, the velocity of the center of mass, is just dr by dt. If I differentiate this with respect to time, what do I get? 1 over the total mass times, that's not changing with time. Well, if bees were leaving or entering the system, then the total mass might be changing, but that's not what I have in mind. I'm stuck with this collection of bees. Nobody is joining and nobody's leaving. These bees are just swarming all over the place. So the total mass is a constant, and the mass of each one is a constant. They're not eating or whatever for of these two, dri by dt. That, of course, is the velocity of the ith bee, so this is 1 over capital M times the sum of mi times vi, the velocity of the ith bee. Big deal. I'm going to rewrite this slightly, pulling the m over to the other side. Then what this tells me is that the sum of the masses times the velocities of all of these is equal to the total mass of the whole swarm times the velocity of the center of mass of the whole swarm. What does that tell you? This here I would read as the total momentum, the sum of the momenta of all of the individual bees in the swarm. If I add up the momenta of all the individual bees, I get a number which is equal to the total mass of the whole swarm times the velocity of the whole swarm. It's as though I could pretend that all of the bees, all of the mass of the bees was concentrated at that one fictional point, the center of mass, and then I watch how that moves, and I come up with exactly the same momentum as if I had gone in there and examined every single bee and added up its mass times its velocity. So, you know, we've kind of implicitly used that. In fact, what I'm doing for a moment now is, in a sense, confirming what we've been doing by the seat of our pants without ever thinking about it. When I asked you, what is the momentum of a basketball moving along? You just said, well, what's the mass of the basketball? And multiply it by the velocity of the basketball. You did not stop and say, wait a second, that basketball is made out of a whole lot of little atoms and molecules. I better look at each atom and molecule inside the basketball, find the momentum of that, and then add them all up. That would be a laborious procedure. What this tells you is you don't need to have to do that. All you need to do is take the total mass of the basketball, multiply it by the velocity. The velocity of what point on the basketball? The velocity of the center of mass of the basketball, if you want to be absolutely precise about it. Multiply the total mass times the velocity of the center of mass, and you will get the same number as if you had added up all the momenta of each of the atoms that goes to make it up. It's what, as I say, we've been doing by the seat of our pants, but unfortunately, it happens to be valid. Okay, let's differentiate again to get the acceleration of the center of mass over to this one. The acceleration of the center of mass, A, capital A, because it pertains to the whole object, is dv by dt, which is, here's v, it's 1 over m times the sum of mi d little vi by dt. But that's nothing but the acceleration of each one separately. You see how the story goes. mi ai. So the mass times the acceleration of the whole works is the sum of the masses times the accelerations of each of the little bits that goes to make it up. Well, mi times ai, what would we call that? Mass times acceleration. That's the force acting on the ith particle. I'm going to call it little f sub I because I'm using little letters to denote things that are happening on each of the individual bees. So this tells me that the sum of all the forces is equal to the total mass times the acceleration of the center of mass. Now this is not quite as nice as you might think, because what are the forces acting on individual bees in there? I can think of it like this. If I pick out a particular bee, it has two kinds of forces acting on it. There are external forces, like the force of gravity or the force of the wind blowing on it or something like that. And then there are internal forces due to other bees in the swarm. Their gravitational attraction for one another or whatever, bees don't interact that much, I guess. Well, maybe they do, I don't know, but maybe imagine that they're electrical charges or something like that. So they're actually exerting forces on one another. It could be. Anyhow, what I'm trying to say is that the force acting on the ith bee can actually be thought of as consisting of two parts. The external force acting on it due to agencies outside the swarm, and the internal force acting on it due to all of the other bees in the swarm. So Fi is equal to Fi external, I'll call it, plus Fi internal. Due to external agencies, for instance, gravity. I'm not talking about the tiny gravitational attraction of the different bees, the attraction of the Earth. Why is this a convenient way to chop up the total force? Because what I had to calculate over here was the total force. This is going to be the sum of the external forces plus the sum of the internal forces. And the whole thing is equal to the total mass times the acceleration of the center of mass. What's the point? This term is equal to 0. The sum of the internal forces is equal to 0. Why is that? Newton's third law. Somewhere in this sum, I have the force of B number 13 on B number 27. Somewhere else in this sum, I encounter the force of B number 27 on B number 13. And those are equal and opposite. They always come in equal and opposite pairs. That's the beauty of the internal forces. They're always in equal and opposite pairs. So this sum is equal to 0. I don't want to write that out in detail, but is the argument there clear? If I talk about a single particle, a single bee, the 27th bee, the sum of the internal forces on that is certainly not 0. But if I say the total, the sum of all the internal forces acting on all of the bees, that's going to add up to 0, because for every force of one bee on another, somewhere in that sum, there's the force of the other on the one. Those are equal and opposite by Newton's third law. So Newton's third law guarantees that this term, the internal forces, exactly cancels out. And what am I left with? I'm left with the fact that the sum of Fi now, not all of it, but just the external part, is equal to the total mass times the total acceleration. Or, if I care to write it this way, let's call this whole thing the total external force. That simply is a shorthand for the sum of all the external forces acting on each of the bees in the swarm. What does this tell me? Again, this is something that we have actually been using all along. In fact, if this were not the case, physics would never get off the ground. What does this tell me? If I want to know the motion of, say, a falling brick, if you think about it, that brick's very complicated structure in terms of all the atoms and molecules that are in there interacting complicated ways with one another. But none of that matters. If I want to know about the motion of the center of mass of the brick, the mass times the acceleration of the center of mass of the brick is exactly the same as if I pretended that only the external forces were acting and added up all those external forces. So it's the force of gravity on atom number 1 plus the force of gravity on atom number 2 and so on, add them all up for the whole brick. But I don't have to inquire, how about the force of atom number 27 on atom number 39? That all disappeared in the summation here. What this tells me is that for the motion of the brick as a whole, I can forget completely about all the internal forces. That's the magic of Newton's third law. I remember we used to have discussions, not at this level, but more like sort of junior level in physics, about Newton's third law. You know, what has it done for me recently? Fact of the matter is, we seldom invoke Newton's third law explicitly, but it underlies everything we're doing. And here's maybe the cleanest example of that, that you wouldn't have a prayer analyzing the motion of a falling brick if it weren't for the fact that all those internal forces cancel out because of Newton's third law. So the motion of the brick as a whole, mass times acceleration, is exactly as though only the external forces applied. You can pretend that that brick is entirely located at its center of mass and analyze the acceleration of the center of mass, putting all of the mass there and pretending that all of the external forces act at the center of mass and forgetting about all the internal forces. Let's see. I know, I wanted to give you a warning now. Students very often at this point say, well, that's a relief. What this tells me is that all of physics, you know, if you've got some complicated composite structure, just pretend that all of its mass was concentrated at the center of mass and do business with the center of mass, and you'll come out with the right answer. This is true for momentum. Here it is. It's true for Newton's second law, F equals ma. Moreover, in the case of Newton's second law, I don't even need to worry about the internal forces, just the external forces. But it is not true for kinetic energy, for example. Said that very well. That is not the case that for every purpose you can pretend that all the mass is concentrated at the center of mass. Here's a warning example. I mean, it's obvious when you think about it, but suppose that I had two masses and they're approaching each other with the same velocity, v, m, and v, like that. And I asked you, okay, what's the total kinetic energy of that system? K equals 1/2 mv squared for one of them, plus 1/2 mv squared for the other one. That's mv squared. Unambiguous. But suppose that you were naively saying, well, to calculate momentum or to calculate force, let's say also to calculate kinetic energy, I just pretend that all the mass is concentrated at the center of mass. What would you have got then? You would have said K is equal to 1/2 the total mass, 2m, times the velocity squared of the center of mass. Wait a minute. What's the velocity of the center of mass in that case? 0, huh? The center of mass is not moving. The center of mass is actually right there in the center. So V is equal to 0 in this case. And I would conclude, if I was naive about it, that the total kinetic energy of this system is equal to 0. For calculating momentum, this would never happen to you. If you want to calculate the momentum, you've got two choices. Stick all the mass at the center of mass and multiply that by the velocity of center of mass, or calculate the momentum of each one separately and add them up. You're guaranteed to get the same answer. If you're doing this with kinetic energy, you better be careful. The total kinetic energy is the sum of the kinetic energies of the individual bits, and that is not equal to 1/2 the total mass. times the velocity of the center of mass squared. Enough on that? So that's just a warning that you not overread the situation here. There are a large class of problems that are based now on Newton's, what I call Newton's second law for a collection of objects, which is what I've written up there. The mass times the acceleration of the center of mass is equal to the sum of the external forces acting. If the sum of the external forces is equal to 0, and the center of mass was initially at rest, then the center of mass stays at rest, right? Because if F external is equal to 0, then the mass times the acceleration of the center of mass is equal to 0. So the center of mass is moving with constant velocity. But if its initial velocity was 0, then it stays 0. So where are we? In particular, if F external is equal to 0 and the center of mass was initially at rest, then the center of mass never moves. This is a handy realization, and as I say, a whole lot of problems when you do an example. An example that will be painfully familiar to anybody who's worked a bit around boats. Suppose that here's a dock, and you sailed your boat up so that it's just bumping into the dock, and here you are, you're in the stern of the boat, and you want to get off. And let's say the boat has a mass m, and you have a mass little m. What do? You walk along the boat. Let's say that the boat's length is L. You walk along the boat, but to your surprise, when you get to the bow of the boat, you find that you can't just step off here. Why? Because the boat has meanwhile moved out from under you, and you're now a little distance from the dock. Why is that? Because the center of mass position, where is the center of mass of the boat person? The center of mass of the boat would be, let's say that it's a uniform boat like a canoe or something, it would be right at the center. And so the center of mass position of the combination would be somewhere like that, a little bit shifted over toward you from the center of the boat. And that position is going to stay fixed. So a moment later, when you've walked down to the front end of the boat has meanwhile recoiled over here. So there's you. You're now, you're surprised, a distance d from the dock, not right up next to the dock where you thought you would park, because the center of mass now is a little bit to the left of the center of the boat because you're over in that location. How far, in point of fact, are you from the dock? In the first instance, the center of mass was 1 over the total mass, m plus little m. Lousy notation. I shouldn't use capital M for the boat. Shall I change it to MB or something like that? Or can you handle this? I've usually used capital M for the total mass of the whole works. Here, capital M. The total mass is capital M plus little m. What is the center of mass now relative to the dock? Let's measure x over from the dock. Well, I've got the boat, mass m, and it's at position, well, its center is at position L over 2. And I've got me at the back of the boat, and my position is L. So that was the original center of mass. In this configuration down here, what was the center of mass? Over the total mass times. Now I've got me on just a distance d to the right, and now there's the boat, and how far is the center of the boat from the dock in that configuration? Can you read it off?
L plus D.
Not L plus D, because the center of the boat is, this distance here would be L over 2 actually. So D plus L over 2. That's where the center of the boat is. The center of mass does not move because the total external force is equal to 0. Do you believe that? Well, there's gravity acting down, normal force acting up, but those two cancel each other. Why did I do this with a boat instead of with some kind of cart parked on gravel or something? Well, I was trying to get all the friction out of the system. So there's no external horizontal force acting on this system. So X initial must be X final, because originally the center of momentum, the center of mass was equal to 0 when I just pulled into the dock and stopped there, and there's no external force. So X final is equal to X initial. The center of mass does not move. Therefore, this is equal to this. Well, the factors out in front are going to be the same for both. So what does this tell me? It says ND plus capital ML over 2 plus capital MD is equal to ML over 2 plus little m times B. Whoops. No, little m times L. Actually, m times L over 2 cancels on the two sides, and I conclude m plus capital M times D is equal to, on the right, I've just got ML, or what I was trying to find out is how far am I now from the dock? D is equal to M over M plus capital M times L. So that's how far I now am from the dock, because the center of mass of the boat-me system doesn't move in this process. As a matter of sort of putting in reasonable numbers, suppose that the boat is 20 feet long, and the mass is, I'll make life nice for myself and assume that the mass of the boat is 4 times the mass of me, 4 times my mass. Then what would I get? D is equal to M over M plus 4M times 20 feet, M over 5M, 1/5. 1/5 of 20 is 4. Sorry, you've got now 4 feet of open water between you and the dock. There are a number of other examples. I think there are actually 2 on the homework assignment, 2 on the OWL assignment for Monday that are based exactly on this general idea that if the external force is equal to 0 acting on a system and the center of mass was initially at rest, then the center of mass stays put, and that enables you to calculate how when things move around internally, how they move. I have a second to come back to the problem that I wanted to do, but I wasn't dead sure whether there would be time. That was the center of mass, the problem that you'll have on the assignment. Essentially, the problem that you have on the assignment. The center of mass of a semicircular plate. I'm not going to do the whole thing, but just enough here to give you a start on it. What I need to do is calculate x equals 1 over the total mass of the plate times the integral of x dm. How do I do this? I cut the plate into slices now. Out at a certain distance x from the origin, and let's say with a thickness dx. And let's call this distance y. Then what is the mass of that, what do you call it, that strip? dm is the mass per unit area in this case, m over a, let's say, times the area of the strip. What is the area of that shaded red strip now? Its height is y. Well, no, its height is 2y, and its width is dx, so it would be 2y dx. Make sense? What's the area, by the way, in this case, the area of that plate? Let's give it a radius r. 1/2 pi r squared, right? Half pi r squared because it's only half the plate. Okay, are we in business now? This is 1 over m times, this is a dm that would come outside the integral, or m over a and the 2, and what's left is xy dx. Integrate that between the limits 0 and r. This time, what is y? You can use the same ritual, essentially the same idea that I used for the sphere, only then it was r that we were talking about. This is capital R, this is x, and this is y, right? So x squared plus y squared equals r squared. That tells me then that y is equal to the square root of r squared minus x squared. Stuff that in here. Here, so 2. Where? Here? It is. Where did the 2 come from?
No, I just wanted to know if that's what it was.
Yeah. That's the height of this thing was actually 2y.
Yep.
So m's cancel, I get 2 over a times the integral of x times the square root of r squared minus x squared dx, evaluated between the limits 0 and r. That's essentially the fact. This is a little bit tougher integral than the one we encountered before, because it's a square root. Can anybody spot the integral of that? Offhand? It's something or other here to the 1/2 power. Suppose that I guessed r squared minus x squared to the 1/2 power. I want to crank it up by 1, which would make it the 3/2 power. That's close, but it's not quite right. If you differentiated that, what would you get? Not 2. You know, I never can get these things in
Multiply by
advance.
the
I
reciprocal.
take this.
Multiply by the reciprocal.
Times 2/3, 2 over 3.
You're getting closer.
Divide by
It's actually minus 1/3, as I remember. The way to test is just try differentiating it. What would I get? 3/2 r squared minus x squared to the 1/2 and times the derivative of what's inside, which is minus 2x. The 2's actually cancel, but I've got a minus sign and a 3 that I don't want. So make this minus 1/3 and evaluate it.
David, the x dx combination is
Yeah.
very helpful in there because it's the derivative of
Absolutely.
x squared. So there's an analytical way. You can take z or some other weird enough letter equals r squared minus x.
Yeah.
This would
And
be
then
a
it
clever
turns
trap.
out to be a power in.
Absolutely. By the way, if this x had not been there, and you just had the square root of r squared minus x squared, that's a 10 times worse integral to do, tougher integral.
Don't you have to multiply by
X out there is actually staging. So Herb's notion is let x squared equal u, for instance, and change variables.
Or even better, r